thank you very much for the opportunity to sharing our recent works on the Josephson diode, field effect Josephson diode of our group. I'm Peihao from Singapore University of Technology and Design. And I would like to acknowledge my cooperators, Professor Yixing An and Professor Qinghua Li. We are an international group with some professors in China. And our preprint is now available in archive. So this is my outline. I will first give a brief introduction to the Josephson effect and our motivation about the Josephson diode. So and then I will give our basic mechanism for what is the gate tunable Josephson diode, and then give two examples about these systems. A summary will be given in the final section. So first, let me talk about Josephson's effect. So when we talk about Josephson's effect, we are talking about a system containing two superconductors that is in between there is an insulator or a conductor or whatever, can be a topological insulator if you like. The key ingredients is that there is a phase difference between these two superconductors. When the phase difference is non-zero, there is a current flowed in this junction. This is called the current phase relation, which is usually derived by these equations. As you can see, this sign equation, the current phase relation, we can define a positive critical current and then a negative critical current. So because of this curve, you can find that these two critical currents are always equal to each other. So there is no diode effect in these systems. But is that a little bit weird to talk about a diode in a Josephson junction? Because when we talk about diode, we usually talk about a semiconductor diode. It's obvious that the current flows in one direction with very low resistance, and then for the opposite, the resistance becomes measurable. This is a building block of our modern electronics, our smartphones, our something like LED, are based on this semiconductor device. But as you can see, the key drawback of this device is that the inevitable dissipation in this system, because the resistance is everywhere, especially when we have a circuit, this dissipation becomes huge. So problem that can be converted by the superconducting diode in a recent experiment. In these systems, there is a supercurrent without resistance flow in one direction, but with a comparable small resistance in the opposite. This dissipationless current is carried by the Cooper pair. So as you can see, there is some systems using a box superconductors. One direction, the current is carried by the Cooper pair, and the other direction, the Cooper pair is destroyed. So this is called the superconducting diode. We also can see there is a Josephson diode in this system. So the current and the voltage curve is something like this, and we can define the critical current of these systems. The negative one is not matched with the positive one, so the eta here, the diode efficiency is non-zero. So there are many systems supporting this Josephson diode effect, from the topological semi-mental systems, very new and fancy system, and then twist bilayer graphene. They are realized in some recent experiments, but in some classical systems, I mean the semiconducting system, we also expected that there is a Josephson diode effect inside. So in all of this system, not include the system I show here, the key ingredients are the spin-optic coupling and the magnetic field. These two ingredients will create a finite momentum group pair, and this finite momentum group pair will eventually provide an additional current to the critical current. So this is quite simple, that these two critical currents are derived from each other. A simple physical picture is that there is a Meissner effect there is a Meissner effect created by this magnetic field, and this Meissner effect will create a supercurrent flowed in this direction, additional to the reciprocal Josephson diode. So the system become non-reciprocal. So there is a diode effect, and we can see that this Cooper pair current is proportional to the Zeeman field. So another proposal that is proposed is that we can create a diode effect without the need of the external magnetic field. Because we use a Zeeman field using this ferromagnetism to replace the external magnetic field. But even in this system, we also need external magnetic field to tune the diode efficiency. As you can see that the diode efficiency will be decay as the magnetic field is increased, because this is normal. Magnetic field can potentially destroy the superconductivity. So that is one of our motivation. And the other motivation is that when we constructing a circuit, the magnetic field to the circuit, to the entire system is global. It is hard for us to individually tune each part of the system. So what is expected is that if we can have a gate tunable diode that is allow a local gate control, a Josephson diode, and a finite momentum Cooper pair. And the other aspect is that we need to enhance the diode efficiency. To my concern, most of the experiments realized Josephson diode is about 13% with the diode efficiency, even though the system is with some stable design, the diode efficiency can be increased. But this device is a little bit, to my concern, is a little bit hard to realize, I think. So we need to find a simple device with a high diode efficiency. So that is our motivation. Let's talk about some mechanism. We propose a mechanism based on an isotropic spin momentum locking state. So what is the spin momentum locking? That is that the spin of electron moving to the right is with the same velocity to the left. So then isotropy means that the spin up move faster and spin up gets slower. So the faster one, when we consider a superconductor, will gain an energy, superconductor gap move upward, and then the slower one will goes backward. So this is called the Doppler energy shift. And we will find that this Doppler energy shift is related to the Cooper pair momentum with this equation. The Cooper pair momentum then become gate tunable effect. So when we construct a Josephson diode, we will find that this system can be controlled by a supergate acting on these two superconductors and a tunneling gate. This is gate tunability. So let's move fast. We can calculate the current of this junction and find that there is another contribution from the Doppler energy shift contributed by E, or also the energy. Okay. Oh, sorry. And okay, sorry. And diode efficiency. So based on this mechanism, we propose a quantum spin Hall insulator with time reversal broken perturbation. So one of its edge can be divided by an isotropy helical edge state. So we can construct this system as a topological Josephson diode with a diode efficiency up to 14% in theory. But that is not high enough, we guess, because this system contains two edges, so it can become a double edge interferometers. By locally control these two gates in each edges, we can
twin the die efficiency up to 90%, it actually is based on a zero temperature system. So this is for our, to the best of knowledge, is the record high value of the die efficiency in the theoretical proposals. But our next question is about, is this a topological system? So of course, it's not based on the topological system. In the preparation of our work, we find that there is a recent experiment based on the semiconductors that is allow a gate tunable effect. We find that we share same mechanisms by making some mathematical works. So we eventually find our theoretical works have an excellent match with the experimental data, including some gate tunability and the maximum and the minimum of the magnetic field direction match with the experimental results. So that is my summary. We put forward a mechanism to support a gate tunability Josephson diode, and then propose two systems that can be realize this mechanism. So thanks for your attention. So I would like to show that our group is still hiring some postdoc position. So if you are interested to our group, please feel free to let us know. Thank you very much.